Hello, everyone. Very excited to be here to talk about Rust for a little bit. There's not enough Rust talks yet, so let's do one. I was actually expecting there to be more, but I can be the first, I think. So before I start, I really wanted to know how many of you are using Rust, like on a daily basis? Okay, so not that many. That's great, because then I can talk about it. So about me, I'm Bas Zalmstra. So this is my Twitter handle. I hardly ever tweet, but yeah, it's still there. I'm part of the Prefix team, and I used to do game development for quite a while. But then I did a stint in robotics for 2 years. But I've always worked on development tooling, like tools for artists, tools for roboticists, and packaging is something that I've been doing since robotics, really. And then Wolf actually came up to me and was like, can we do this in a better way? And I was like, yes, let's do it. Let's build new development tools. So yeah, Prefix, shortly about what we do. We build package management software, and we want to make it as easy and painless for everyone. Wolf has like a very long background in this, so he started this. So why do we use Conda? We do use Conda as our tool of choice. Why? Because, well, it's easy to use multiple languages. You can use C++, Python, or R, or anything really. It's a language agnostic. It supports a lot of different platforms. So we have very good Windows support on Apple and Linux. And there's glibc there because we basically work on any Linux system that has a glibc version, but I think we can also work without it, actually. We have support for multiple architectures, so there's ARM, we can use x86 and some more, and also WebAssembly, which is also kind of nice. I think there's like a lightning talk about it today or tomorrow. Conda uses also a set solver to thank you, Todd, for explaining that already. Conda is deterministic in the sense that we don't remove any package artifacts. It's a binary package manager, package management system. And we build basically on Conda Forge, which is an open source distribution, and I will talk about that a little bit more. So who's already using this? So in data science world, it's used a lot. It has great Windows support. Machine learning, because we have actually pretty good GPU support. You can install CUDA stuff with it as well. It's used in robotics a lot. Well, not a lot, but it's starting to grow more and more because it's very easy to combine both your C++ and your Python together in a single environment. And yeah, cloud deployments, because it just runs anywhere. And I don't want to talk too much about why we chose binaries over source, but because yeah, our users care about running the software, not so much less building the software. Todd also mentioned already, like, building is hard. So if you want to read more about this or learn more about this, Ashley Williams gave a really good talk about this at Eurorust. I think you can look it up. So I already mentioned Conda Forge briefly, but it's an open source distribution that builds Conda packages, and it's really great, to be honest. It has already 23,000 unique packages in there, 2 million artifacts, so different versions, and it's maintained by 5,000 plus contributors. So there are a lot of different people that provide recipes that we build certain software into artifacts. And there's much more. So we have migrations to easily migrate to new Python versions, for instance, or new CUDA versions. There's bots that automatically create new releases if new releases are available for software. And we can do repo data patching, which means we can retroactively change some of the upper bounds, for instance. So if some of the things break because people didn't actually put their upper bounds correctly, then we can actually patch that retroactively, which is kind of useful sometimes. A little bit of the history is that Conda, it was initially, I think, developed at Anaconda, and it's a Python. It's both an ecosystem and a package manager, and it's initially built in Python. And then at some point, as it became larger and larger and larger, the solves for these environments became like very long, like minutes or even very long. Someone, Wolf again, built a new package manager called Mamba, together with at Quantstack, and they're still working on that. And it's been developed in C++, and it uses an existing solver called libsolv, and more on that later. At the meantime, I was working at a robotics company, and we wanted to use this Conda ecosystem as well, but we wanted to interface with some of the Conda APIs, and that wasn't really available at the time. So I started building in my spare time a Rust implementation of everything Conda, and we call that Rattler. And at Prefix, we've been working on that more, integrating more, and at this point, it's able to do, I think, almost everything that you want to do with Conda. Where do we use this? Well, it's been used by us in a couple of different places. So the prefix.dev website, it's a package index where you can search for packages and get all the information for all the packages that sort of exist, at least for Conda Forge and some other sources. And we use Rattler in the backend to read all the package information, to parse the versions, parse the specifications, and all sorts of stuff. And Rattler server is a web server that you can spin up to solve environments, and that does it pretty quickly in seconds, less than seconds. You can use that over HTTP, and Rattler is also powering that. Then we have Rattler build, which is a application to build recipes, which are sort of how you convert source to a binary. And Conda build is an existing tool that's used everywhere, and we're trying to replace that or building a new tool, Rattler build, that's much faster and builds on the Rattler ecosystem. Then we have Rattler OCI to build OCI images directly from Conda environments that provide great caching, because you can cache, each layer can contain a package. And then Conda Rattler solver was not built by us. It's a Python plugin for Conda, the package manager Conda, that uses the Rattler solver instead of the Conda solver, and there's also the Mamba solver, but that's another story. And last but not least, we have Pixie, which is the modern Conda package manager that we are developing. So a little bit more on that. So Pixie is, so Conda has been around for a long time, but the workflow that you use to work with Conda hasn't changed that much. Whereas there are a lot of new package managers, like Cargo, NPM, Yarn, Poetry, and you name them, and they all provide like a different workflow that's more optimized or simpler for most people. And we also try to bring that to Conda. So if you install Pixie, it becomes really, really simple to interact with the Conda ecosystem. And it's also blazingly fast, and I have to say that because it's written in Rust. It's very easy to install because it's just a single binary. You can just put it on your PC, and that's all you really need to do. So there's no shell hooks that you need to integrate or configuration files or stuff like that. It's also built on Rattler, of course. But the main thing that we are trying to achieve here is something that you can do with a lot of modern package managers. It's basically you take a repository, you git clone it, and you can Pixie run it, and it will install all the dependencies for you and run the application. And that works on any machine that the project supports, which is pretty cool. So why Rust? So yeah, I can name the default things that you hear everywhere, like it's safe, safe memory access, threading is easy, it supports async with an asterisk. It's cross-platform, it compiles to a single binary, and again, it's blazingly fast, which is all true. But for us, the most compelling thing for using it is because of the ecosystem that exists. Like, it's very easy to use crates, so packages, and they are pretty high quality. So we use a lot for serialization, and I'll get to that a little bit more later, for networking, for decompression and compression, for file system access, and CLI utilities, and all of these testing things that are around. And this really helps us focus on what we want to do. We want to build a package manager, and we don't want to go into the nitty-gritty of how a certain operating system works. So I mentioned async briefly, and Kat was also mentioning this, but async is really nice. Like, the code that you can use to express async things is really, well, pretty readable. But it's not for everyone, so yeah, Kat already mentioned this, but the file systems async file system access doesn't really benefit. It's easier to, or faster to run these blocking operations in a per thread CPU, per processor, no, per CPU thread. And it also, like Rust is already pretty complicated with the borrow checker, and it becomes even more complicated if you're also having memory that is accessed in the background by some task, and yeah, that doesn't really help. Like this example is great, but it's often more complex than that. So Rattler, I already mentioned it briefly, but it's sort of an ecosystem of all sorts of different things. Like we have a bunch of different crates that all sort of solve certain problems within the ecosystem. And then we have some like external things around here, like we have PyRattler, which is basically the Python bindings to all of this. And Resolvo is the solver that we developed, more on that later. And then there's also Rattler installs packages, which has nothing to do with Conda, but it's a thing that we use to solve and work with the Python and PyPI environments. Also more on that later. So one of the things that we do with Rattler Conda types, which is one of the crates, is that we try to define like strict data types, because in Conda, formal definitions and schemas are missing. Like they're being worked on, but they're not like very explicit. And we've encountered this because we were indexing all of the Conda packages, and we encountered like really weird situations. But yeah, we try to capture all of these into structs, and those structs, then we can really serialize easily with from JSON or any other format. And we also implemented all of the weird and undocumented behaviors that Conda has. So you can have a trailing underscore in a version, but only if it contains dashes and no other underscores. So one dash is not valid, one dash underscore is valid, one underscore is a valid version. There's really weird scenarios. And sometimes we also have to make opinionated decisions. For instance, what does larger or equal than 3.4. actually mean? Yeah, we see those things. I have a few more examples later. But one of the crates that we use from the ecosystem is serde. And if you've used Rust before, you might be familiar with this, but it's really easy to implement serialization and deserialization from different formats. So I have a little example here. It's a point, it contains X and Y. And all you need to do is basically derive, serialize, and deserialize from it, and that implements everything you need to serialize to a whole bunch of formats. So that you can use it like this. So you have a point, you create it, and you can say serde JSON, which is a great also to convert stuff to JSON, and you just give it a reference to that thing, and you got JSON. And deserialization the other way around is just as simple. This is really powerful. And we use it everywhere. So we have a lot of different types to sort of formalize the ecosystem, and they all implement like serialize and deserialize. Sometimes we use these attributes to make it, to serialize it into a better data format that we can use. Yeah, so lots of it. And we can also perform normalization on while serializing or deserializing. So for instance, this is something you encounter often, like a development URL, like what's going to be the type here? So you can have a URL, that was the initial implementation, and then we try to parse it, but sometimes the HTTPS is missing, sometimes it's comma separated, sometimes it's actually an array, and weird scenarios. So we try to do our best to sort of find all these weird edge cases and try to turn it into a proper type that we can then have a typed struct. Is another example where you have timestamps in Conda, but sometimes they are expressed in seconds since epoch, sometimes they're expressed in milliseconds, and sometimes they're actually mixed in the same file. It's really weird. So what we do is we basically always convert it to a date time, and then while serializing, we basically do this conversion, so any user of these types doesn't have to care about this. Another great example is all of the metadata that's used in Conda is stored in repodata.json files, and they become really, really big. Like for Linux 64 channels, they are 250 plus megabytes of raw JSON. And we need to parse that to be able to solve it. But most of the time, you only need a very small percentage of all the package information that's in there. So if we would naively deserialize this, then we would deserialize it into a mapping from a string to a package record. And then if we load that information, all of it is loaded. And even in the blazingly fast Rust, this can take 1 to 3 seconds, which is already too slow. So one thing you can do here is to use raw value, and it's still a mapping here, but it's stored in a vector instead of a map. But the raw value is just a pointer to the to JSON, raw blob JSON in the file. So when we deserialize this, we basically iterate over all the keys, but we do not actually parse the objects. And this makes it much faster. We can do this in 100 milliseconds. And then we can extract like the information, like if we only need Python, for instance, we can take only the records for Python because that's in the file name, and then only then deserialize the Python records. And this improves the performance significantly because, yeah, it's just a lot of data. Another thing that we've developed is Rattler solv. This is a crate that defines a common interface basically to implement multiple solvers for the Conda ecosystem, but with a single front end. So if we want to solve stuff, we basically create this task, which contains everything that goes into solving an environment. And we give it to 1 or 2 backends. So we have libsolv and resolvo. And libsolv is an open source SAT solver. It's used in DNF, the successor of YAM. And it has been adopted, to work with Conda as well. The main maintainer, I think, of the library implemented Conda support overnight. And this is actually what powers Mamba. That's what makes Mamba so incredibly fast compared to Conda. And Rattler also supports this. So we create auto-generated C bindings to interface with libsolv, so you can also use libsolv in Rattler if you so choose. But the Conda implementation in libsolv is actually incomplete. The one that Mamba is using actually has some additional patches on top of it to make it work correctly. And these patches are in an open pull request to libsolv, and they haven't been merged, and they are open since 2021. The other thing is libsolv is really, really hard to understand. It's very low level C where the 31st bit means something more often than not. It's very algorithmically complex because, yeah, set solvers more often than not are pretty complex. And there's little to no code documentation in the C code, which makes this not great. And it's only maintained sort of by one person, which is, the image highlights this pretty well from XKCD. If this sort of falls over or if something weird happens, then we as an ecosystem are pretty much, you can fill in the last word. So we set out to try and build something that we can also maintain, preferably something that already exists. But yeah, not everything is written in Rust, which makes this difficult. So we've been looking at taking an existing solver and sort of porting that. So we've looked at resolvlib, which is the solver used by pip. We ported it to Rust. It's open source, you can look at it. But for us, it turns out to be too slow for some of the edge cases involved in Conda, because some of those complex cases contain more than 500,000 candidates that you have to account for. And the resolvlib backtracking is simple, so to say, in that that didn't work for some of those edge cases, which was a pity. So we looked somewhere else, and Kat already mentioned this one. So we have pubgrub, which is a really good solver written in Rust, and probably one of the best libraries I've ever seen in terms of code quality. But yeah, for Conda, unfortunately, it didn't really work because pubgrub assumes that you can express everything as mathematical ranges, 1 to 2, for instance, and you need to be able to compute intersections and unions. And for numerical ranges, this is relatively easy to do, but for Conda, this is very complex because we also have multiple things that you can match on, and these things can be regular expressions or they can be globs, and yeah, it's pretty complex. And also, PubGrub really requires that if you take like the union or the intersection of A and B, that it results in the same thing as B and A. And if you take the complement of thing, that it returns that it's empty. And so some of these things are really hard to express for matchback. Another thing is that it didn't support constraints or peer dependencies in some of the other ecosystems. I opened the PR for it, but it's not been merged, unfortunately. We also tried to do an experiment where instead of using version ranges in the form of matchbacks, we basically take all the variants that are available for a package. We make like a set of it, and then the version set or the range that we look at is just a bit set where 1 means we match this variant and 0 means we don't match this variant. And then we can very easily compute whether it's empty. We can do intersections, and we can do unions and complements and stuff like that. But there are some assumptions in the solver, and they are being worked on, to be fair, that if you have a set and it contains all zeros, then you don't know if that range that you selected actually just doesn't match any of the versions that that are available, or that it can never match a version. So if you have larger than 1 and smaller than 1, those are 2 ranges that will never result in a version, and that's something that the implementation requires to know. But I think Jacob is also listening along. I would love to talk to you more about this. But yeah, so this wasn't a solution that we could use. So we have been looking at, well, porting something else. And we've been looking at libsolv, which was the hardest thing to do because of this very low-level C. But the initial implementation that we made was created by Adolfo Ochagavia, always difficult for me to pronounce. And it's mostly inspired by the Miniset papers on which libsolv is also based. But it's not just a set solver, it's adapted for dependency resolution, because we don't want to find just a solution, we want to find the best solution. So in this case, you have foo that depends on some version larger or equal to bar, and it can either be 1 or 2, doesn't matter. Both of those are solutions in the set solver, but we want to find the one with the highest versions. But that can become very complex if you have this case where now bar 1 requires Bas 2. So yeah, there's not really like a proper solution here. Well, there is, well, yeah, I don't know. You have to make some decision here. We've also, besides actually porting it and calling it Resolvo, we've also optimized it. So for some of the edge cases in Conda where a lot of backtracking is performed, we were able to increase the speed up to 5 times by implementing some heuristics where we say, okay, if you have to make a decision about which package you're going to try next, let's try the one that causes the least amount of conflict. And this really optimized it a lot. And we also made it hybridly incremental. So we can also solve, libsolv requires all metadata to be available upfront. But if you are going to solve PyPI, for instance, then this metadata is not available, and it's also very expensive to request. So we need to make the solver in such a way that we can sort of get a partial solution, get all the information to get to a complete solution, and then that also works. And finally, we made it generic. So instead of it relying on Conda or DNF or RPM, we use a trait that you can implement for an ecosystem that implements like the ecosystem-specific complexities, and the solver is just unaware of these, and it can be used for different ecosystems, which we used to create another library, RIP, Rattler installs packages, to solve Python packages as well. And RIP is a very bare bones pip implementation that actually works. And it uses Resolvo, and it's able to really quickly resolve Python packages. But yeah, the biggest problem there is also getting the metadata, so that takes up most of the time. We can parallelize it a little bit, getting the metadata, but not all of it. And we are also integrating this into Pixie itself, so that we can solve for Conda and also for PyPI, and you can create an environment that combines these 2 ecosystems, because we're really trying to bridge the gap there. And it's kind of nice because then you can install your Python packages from PyPI, but get Python from Conda Forge and install all of the system libraries as well, including CUDA. So what's next? We're going to continue on improving Pixie a lot. There are a lot of features that we want to implement. We want to try and get source dependencies there as well. So your Pixie project can also depend on other Pixie projects, and then we build from source. And we want to make it more easy for everyone to contribute to Conda Forge, like make it just so simple that anyone can add a new package to it. And we are doing that by improving the format, improving the error messages, just general developer experience. And we're doing that in Rattler build. So to quickly recap, and then I'm done, I promise. Rattler is a modular set of APIs that you can use to do everything Conda. And it's relatively easy to reuse because of Rust. There's great documentation. And we hope that it facilitates a new set of tools that anyone can use. Pixie is one of those tools, of course, and we think it really modernizes the way that you work with Conda. So if you ever use Conda and you're like, this is way too slow for me, I don't know what's going on, then give Pixie a try, because I promise you it's much better. And that's everything. Thank you.
Okay, we're really running behind time today, so I just want to take a couple of quick questions, if anybody's got one. Maybe one from this side and one from that side. Okay.
Thank you. So I was interested to know whether you have considered using CBOR for your repo query.json file, which you mentioned was almost 1/4 gigabyte.
If you mean SQL in terms of like a database that hosts it somewhere, or SQLite? SQL. CBOR. I'm not familiar with that, but that might be a good thing to look at. I won't know.
Do we have any more questions from this side? No?
Yeah.
Oh, one.
I was very interested when you mentioned in your CDCL solver, you said something along the lines of, we don't want just any solution, of course we want the best solution. I'm wondering whether you also want a unique solution, or whether you get that from this, this optimal solution here. Maybe that's probably a simple question. I'm just wondering about that.
So there are multiple solutions for sure. We just want to find the best one, yeah, or the best one. Let's say it like that. So what are our optimization criteria for the solver? Definitely speed is one. But yeah, so we basically look at our heuristics are currently in such a way that we look at, okay, which decision do we need to make? Like we have a bunch of decisions, and we choose the one that has the least number of candidates available, and then we select the highest version of that package. It's still, I think we can improve on that still a lot.
Okay. Thank you, Bas.